Welcome to The Explainer. Today, we're jumping straight into a truly massive deep dive on the absolute physical limits of computation. We're going to look at how a wildly important summer 2026 breakthrough fundamentally rebuilt the way machines process information, literally from the ground up. If you've ever found yourself wondering what's actually happening down at the microscopic silicon level when an AI generates a response, well, you are in the exact right place.
But before we get to the actual solution, I kind of need to shatter a widely held assumption. 80 to 90%. That is a huge number, right? Well, that is a staggering chunk of modern AI compute cycles that simply aren't exact mathematical truths. They're literally just hardware-level approximations.
It brings us face to face with what researchers like to call the grand computational illusion. We all intuitively feel like computers understand the meaning of our words, right? Like they process exact math to give us an answer. But beneath the hood, the machine is completely blind to meaning. It's relying entirely on continuous electrical currents and highly educated mathematical guesses burned right into the hardware itself.
Okay, let's dive right into this. Here's our 6-step roadmap for the journey. 1. The FPU Gambler illusion. 2. Enter the ALU surveyor. 3. Pell-Smith integer sequences. 4. Shattering the trig wall. 5. Bridging to turboquant. And finally, 6. The 0.05 picojoule energy floor.
Starting with Section 1, the FPU Gambler illusion. We've got to look at the physical constraints forcing all this guessing in the first place. Inside your processor, there's this massive divide. On one side, you've got the floating point unit, or the FPU. Think of the FPU like a fast, frantic gambler. It's just throwing darts at a board, using these secret seed tables to give you a really fast approximation of a continuous curve. It's inherently lossy, it's probabilistic. But then, on the other side, you have the arithmetic logic unit, the ALU. This is the surveyor out in the field with a precision laser. It's strictly deterministic. It performs exact, discrete, verifiable math. 1 + 1 = exactly 2 every single time.
The crazy thing is, our current AI models rely almost entirely on that FPU gambler. And as this quote from the source documentation beautifully puts it, the FPU basically acts like a giant digital blender. They call this the wood chipper effect. Because the math is just a lossy approximation, it permanently destroys the exact chain of title and the provenance of the data. You can never unblend that smoothie to see the exact ingredients that went in.
Right, so if we want actual truth, we need to transition away from this lossy, blending observer. Which brings us to Section 2, enter the ALU surveyor, restoring exactness. The fix here is migrating our logic over to the ALU surveyor. The ALU relies entirely on high voltage being a 1 and low voltage being a 0. Boom, that's it. It acts as a globally accountable universal witness. By anchoring our math here, we restore what physicists call Noether's theorem, giving us true symmetry and reversibility. We completely eliminate what the docs call observer debt, which is basically where the complexity of the math exceeds the hardware's ability to perfectly track it.
But wait, how do you run complex AI algorithms, which usually need smooth, continuous curves, on a rigid, integer-only grid? That brings us to that massive summer 2026 breakthrough in Section 3, Pell-Smith integer sequences. It really all comes down to base-scale calculus and OIS integer sequences. Instead of using messy decimal approximations for irrational numbers, like the square root of 2, researchers leaned on Pell's equation. You get these integer ratios, 1/1, 3/2, 7/5, and they form a sequence of convergence. They provide incredibly accurate approximations using purely verified integer logic, no decimal points, zero floating point guesswork. So the crucial point here is that the Pell-Smith stride lets us completely bypass that FPU gambler. We swap out those continuous floating point curves for exact, verifiable rational coordinates. We shift from merely being a lossy observer guessing at a curve to actually forensically possessing the mathematical state.
Now, applying this integer framework to the circular geometries needed for AI takes us to Section 4, shattering the trig wall to get straight, exact lines.
Now, what's really interesting here is the concept of side-A normalization. Traditional AI uses heavy trigonometry, like cosine scoring, to map vectors. That creates this massive trig wall that literally forces the processor to guess. But by anchoring the coordinate system to the transversal constant, where A = exactly 1, we turn those messy curves into straight, exact lines. We shatter the trig wall entirely, operating on discrete reciprocal shifts across a rational lattice.
And this perfectly sets up global remainder tracking, or GRT. By explicitly tracking the exact remainders as a strict machine state in a deterministic loop, the system knows exactly when to stop computing. This mathematically prevents fatal stack overflows and safely enables infinite context AI inference without the system ever drifting off into wild, unverified hallucinations.
Let's see how this all builds into Section 5, bridging to turboquant via the semiotic bridge. We pull this off using what the source is called the semiotic bridge. Think of it as a macro to micro funnel of formalization. Step 1. We start with our messy, fuzzy human intent. Step 2. We format that into strict text. Step 3. We lower that text into a geometric tile matrix on the GPU. And finally, Step 4. We hit pure, unyielding ALU execution. We're intentionally trading expressive human freedom for absolute mathematical certainty on the silicon.
This pipeline seamlessly bridges directly to turboquant, which is a data-oblivious vector quantization algorithm detailed in the recent Zenodo paper. Turboquant takes this strict logic and applies a random orthogonal rotation to the vector. Sounds complex, I know, but it basically compresses the AI's short-term memory, the KV cache, down to a staggering 1-bit representation through Pythagorean packing and metabolic dithering. And the absolute miracle here? It achieves near-optimal distortion rates with absolutely zero loss in accuracy for 1-bit LLM orientation.
Which brings us to the macro real-world impact of migrating from the guessing gambler to the bit-perfect surveyor. Section 6. The 0.05 picojoule energy floor in the era of hyperdeflation.
0.05 picojoules, that is the hard, absolute physical energy floor we unlock with bit-perfect orientation. And this brilliantly illustrates the sheer scale of the shift. A standard 16-bit fluid operation, full of complex, lossy approximations, burns about 3.70 picojoules of energy. But the 1-bit Pell-Smith ALU operation? Just 0.05. That is a massive, staggering 74 times reduction in energy burn. We are literally talking about the absolute hyperdeflation of global compute costs here.
The real-world implications of this are just massive. By achieving forensic finality directly on the exact silicon layer, we completely avoid that 50% critical line where FPU drift makes data mathematically useless. We liquidate observer debt. We establish an undeniable, universally consistent ledger of facts directly on the metal. And because the hardware itself provides absolute proof, the transaction cost for verifying trust drops to near zero.
I really want to reflect on this profound quote from the architecture docs. The human pilot applies the intent, but the agent cell executes the sweat. We have literally bridged the gap. Humans are messy, right? We're imaginative. Silicon is cold, rigid, and strictly mechanical. But through this mathematical framework, we are safely and perfectly translating abstract imagination into unyielding, strictly deterministic physical action. So I'm going to leave you with this thought. We've traced this incredible alternate path from chaotic, hardware-level guessing to bit-perfect, highly efficient, absolute digital truth. With the semiotic bridge now wide open and anchored securely in absolute mathematical reality, what will you program it to do? Thank you so much for hanging out with me for this explainer. Keep learning, keep exploring, and I will catch you next time.